Alright, this is section 4.2, notes, combining functions, composite functions. So combining functions mean we're going to take two functions and we're going to add them together, subtract them, multiply them, divide them. Okay, and notice here that the notation here, they put the f and the g together with a plus sign between them. All that means is just add the two functions together. Okay, they give us an example right here. So square root of x is the first function, x cubed is the second function. This notation means just add those two things together. This means subtract them. This means multiply them together. This means divide them. Alright, provided x is not equal to 0. We can't ever divide by 0. Okay, so this is what we're wanting here. A lot of times they'll ask us for the domain of these things, so we have to understand the domain and how the domain works after we do the operations, because that's where they're going to want the domain done from. So just for an example, if f of x equals that, x cubed, and g of x equals x minus 1, we want to find these following functions. So I'm going to put a couple of them on this first one, then go to the next one. So part A, f plus g of x, that's the same thing as f of x plus g of x. I mean, it's split the two functions apart. Alright, f of x was x cubed, g of x is x minus 1. Now, always when you have these things, especially for subtraction, put a parenthesis around the second one and then decide if you need it or not. We don't need it here, so we just end up with x cubed plus x minus 1. Okay, so there's my combination of these two functions with addition. Now I'm going to do it with subtraction. And notice here when I do subtraction, we have to distribute a negative through. Okay, anytime that your second function has something other than just a single term, if it has two terms, three terms or more, you have to remember to distribute that negative through. So minus x minus 1. And so this negative is going to come through here, get distributed through, and we get x cubed minus x, but minus a minus is plus 1. Okay, so the big thing to remember here is do not forget to distribute negatives. Alright, that's the biggest thing that people make that mistake on this stuff. Alright, and then parts C and D, we're going to multiply these two things and then divide. So part C, multiplying, I get x cubed times x minus 1. Alright, I need to distribute here. So x cubed times x is x to the 4th, minus x cubed times 1 is x cubed. So f times g of x, it just means multiply these two functions together. Alright, so I distribute, but this is what I get. Now, I've left off something from the last one, the domains. The domains are the x values that these things can be. So let me stick those in, and I'll do it on the back side as well. The domain of this function what can x be here? Okay, the domain of this function is all real numbers. We can cube any number. The domain of this is all real numbers. We can subtract 1 from any number. So what's the domain of this composite function? Adding those two together, the domain is still all real numbers, because for any number I can cube it, I can add that number to its cube, and then I can subtract 1. So we get all real numbers for this domain. Alright, likewise the domain here is going to be all real numbers, because once again I can cube any number, I can subtract that number from its cube, and I can add 1 to any real number that exists. So my domain for both of these is all real numbers. Alright, for this one, once again, we're going to get a domain of all reals, because any number I can raise it to its fourth power, any number I can cube, and then those two things I can subtract together. So once again, I'm going to get a domain of all real numbers. Remember, the only time that we have to restrict this is if there's division, and division by 0 could occur, or if there's a square root and some or even root, and some even root of a negative could occur. Alright, so here's the only time we're going to get a domain restriction. When I have f over g of x, that means I got division. I'm taking f of x and I'm dividing it by g of x. So f of x is the cube function. G of x is x minus 1. Alright, so there's the answer to the first part. There's that, but then the domain, remember, we cannot divide by 0. So x can be any real number, but x cannot be 1, because if I put 1 in there, I get division by 0. Okay? Or if I wrote it as an interval, negative infinity to 1, parentheses, union, parentheses, 1 to infinity. Alright, if I wrote that as interval notation, which they're going to ask you to do most of the time for your domains. But because now this one has division, a lot of times we are going to have a domain restriction on the division of two functions. Right? Otherwise, if there's no, especially with adding and subtracting, if there's no restrictions to begin with, there's usually not going to be one when we add or subtract. With multiplication, again, usually you don't get any if you didn't have any to begin with. But with this, that denominator can't be 0, so any value that makes the denominator 0 has to be restricted. Combining these two together this way does have a restriction, even though neither of the original ones did. Alright, average cost function. Average cost is basically one of these types of functions. It's like the part D, the division function. We take a function and we divide by another function. Right? It just happens to be that the bottom function that we divide by is just x. It's just the number that you have there. So according to part A, form the average cost function. So I'm going to say for part A, that's c of x divided by x. So c of x is 50x plus 500 over x. Right? That's my average cost function. That's all I need, but you could split this up. Say 50x divided by 50 is just 50, and then 500 divided by x is just 500 over x. So you could have this, but this is the more traditional way of writing it. So the average cost is given by 50 plus 500 over x. Or again, you could use that one. Alright, part B says, for which input values is this cost defined? Give a real world explanation of this. Alright, now technically, if we're looking at this, this is defined everywhere except when x is 0. But because this is an application problem, the applied domain is a set of all x such that x is greater than 0. Or in interval notation, 0 to infinity. Okay, because it doesn't make sense for this to be negative, even though it could be the way it's written. If this was just y equals 50 plus 500 over x, and we're just getting an arbitrary y value, then yeah, it could be negative. But since this is x represents how many things we're producing, if you look at this scenario, right, number of units produced, then it only makes sense for these things to be positive. Okay, and technically really it only makes sense to be natural numbers and positive. Alright, give a real world explanation of this answer. So that's just basically what we're saying. Since x is units produced, it can't be negative and in the function it can equal 0, or we would divide by 0. Division by 0 would occur. So therefore x must be positive. Okay, so that's what we're talking about. Because it's units produced, we can't have a negative number there. Alright, then part C says graph that for 0 to 500 roses. What can you say about the average cost? So we're going to graph our average cost function. So I'm going to say that's 50 plus 500 divided by x. Alright, and we're going to go to the window. They want us to graph it for 0 for the x minimum to 5,000. Alright, and then we're going to make our scale, let's make our scale go in 500s. Our y minimum, we'll make that 0, and then let's make it go up to, I think we only need about 600. Let's see what happens if that gives us enough. Alright, make that scale 50. Yeah. Now you can't really see it here because y max, let's make that. Let's make that 100 and see if that makes any difference. Yeah, when it's a little bit smaller of a scale, you can see how it's bending right here. But there's what we call a vertical asymptote right here at 0, because remember, it can't be equal to 0. Right? It can't equal 0, division by 0 occurs. So this thing has a what we call a horizontal asymptote, or sorry, a vertical asymptote right there at the y-axis. Right? So what my graph's going to look like then, it's going to be all positives here. So all quadrant 1. So there's from 0 roses to 5,000 roses like they wanted to. Right? When I plug in, I can't plug in 0, but when I plug in something really close to 0, like trace, press the trace button, and then something like 0.0001, I get a really huge number still. Right? 0.0001 gives me still this gargantuous number. But if I go up to, like, say 1, I get 550, and then 2, 300. So if I made this go up to, say, like 1,000, and so there would be 500, there would be 250. So 1 gave me 550. Now this goes all the way to 5,000. So 1 gave me 550 would be like right there. Alright, then ten gives me 100. Would already be, I mean, we're talking about already down to like right here. So there to there, and then it just starts leveling out. If you press the trace button and then start picking big values like 2000. You see we have this, the horizontal asymptote here is going to be that 50 line. So if I put in like 3500, see we're still honing in on 50. So let's say that 50 is about right here. So we had this kind of implied lower floor where this thing can't get below, going across here. And then we have the same thing vertically. So our graph ends up looking something like this. Just hugs the y-axis, touches that point. Touches that point. Touches that point. Hugs the y-axis. Doesn't cross it. Okay, just hugs it. Alright, then it turns really sharp as it gets in here. And then it hugs this horizontal. It gets closer and closer and closer to this dashed line here, but it never touches it. Alright, what can you say about the average cost? What this is telling us is, as the number of roses that we produce gets higher and higher and higher, the average cost lowers until we finally get basically close to that $50 line. We can't get our average cost to go below $50.